Greetings to all and welcome to this lecture. We are in module 6, lecture number 2, Simplified All Region Model 1. In this lecture, we will see the linearization of depletion region charge, and then we will extrapolate this knowledge to define the body reference simplified all region model and source reference simplified all region model. These are the learning outcomes of this lecture, which helps you to understand why linearization is important and how we can reduce the complexity of our preceding defined model. Let's do a quick recap. In previous lecture, we defined the MOSFET operation by this plot. We said that when we are going to plot a graph between Qi dash, which is nothing but inversion charge, and psi s, then we will get some limits of that graph, and between that limit we defined how the current IDS1 and IDS2 flows. So here if I rewrite this equation as Qi dash is equals to minus Cox dash into VGB minus V flat band voltage minus psi s minus gamma root psi s, by putting some extreme conditions such as the value of psi s when Qi dash is equals to 0 is nothing but psi sa, that is what it is, and when the surface potential is equals to 0, then the value of minus Qi dash is nothing but Cox dash into VGB minus V flat band voltage, and that is this point. So we defined two extreme points of this graph. In between, we considered this graph is plotted for a constant value of VGB and we are varying the VDB. Initially we assumed that VDB is higher than VSB, but in non-saturation regime, meaning when you are going to plot the Qi dash versus surface potential, you will get this graph where these points are the solution of these two equations. So the difference between this is Qi dash 0 and Qi dash L, and the difference between this can be calculated as area of this graph, which is nothing but psi s0 psi s L and dq dash minus Qi dash. So this component is nothing but IDS1 and this component is nothing but IDS2. By using this graph, we explained that when we increase the VDB beyond a certain value in the MOSFET, let us say this is VDB, this is drain side, this is source side, and you are increasing VDB beyond a certain value, then the surface potential at this side will increase and ultimately it will pinned to a value of psi sa. Beyond that, the surface potential will not increase. It means the effect of VDB will be lost in current, that is IDS1 and IDS2. So ultimate current is nothing but the area of this trapezoidal. When you increase VDB, this point will shift this side to and forms and collide with VSA. So when it will happen, then the total current can be given by the area of this triangle, which is nothing but constant and does not change with VDB. We have seen in previous lectures that the current can be rewritten as a function of psi sL minus psi s0, and we found that if we change psi sL and psi s0 by changing the terminals of drain and source, then MOSFET shows symmetry. We also derived how to calculate the surface potential, charge and the current as a function of x, in the sense when you move from source to drain. So along this dimension, how you find out the inversion charge as a function of x, surface potential as a function of x, and finally how you calculate the current as a function of x. In this lecture, we will find out how to make simplification in our earlier defined model. If you remember, we defined IDS1 and IDS2 which is nothing but W by L mu into Cox dash into VGB minus V flat band voltage into psi SL minus psi S0 minus half of psi SL square minus psi S0 minus 2 by 3 gamma psi SL to the power 3 by 2 minus psi S0 to the power 3 by 2. That was our IDS1, and IDS2 was given by W by L mu into Cox dash into phi t into psi SL minus psi S0 plus phi t into gamma psi SL square minus psi S0 square. In this, if you see, the 3 by 2 power and 1 by 2 power is coming up. So, this is 1 by 2 power is coming up, which is actually creating a complexity in your model. So, if I want to remove this complexity, I need to go back in the formulation of these equations, and then we will find the power of 3 by 2 or the power of 1 by 2 is coming because of bulk charge, because the bulk charge was written as QB dash is equals to minus gamma of Cox dash into square root of psi s. So, in some places we are using directly psi s as psi SL to the power 1 by 2 minus psi SL psi S0 to the power 1 by 2, and in some places we are doing integration of this psi s to the power 1 by 2, and that is what we are getting 3 by 2 term. So, is there any possibility that we can make a linearization of the square root of psi s that helps to simplify our model? So, in general, in stochastic implicit function method or any Taylor series based sensitivity or variance extraction, we will use some expansion point. Beyond that expansion point, we will linearize our system. So, we will use the same technique to linearize that system. What we are going to do, we can understand by using this graph minus QB dash by Cox versus psi s. So, let me rewrite as QB dash can be written as minus gamma into Cox dash into root psi s. I can plot a graph between minus QB dash divided by Cox dash is equals to gamma into psi s. If I consider a function which is a function of psi s as root psi s, and if I linearize the function around a expansion point using Taylor series method, then I will get, so expansion of let us say x is around a is can be given as f a plus f dash a into x minus a plus higher order terms. So, we can ignore higher order terms and we can simply rewrite this function of as square root of psi s e plus differentiation of this function, meaning 1 over 2 into root psi s e into psi s minus psi s e. So, the expansion of square root of psi s by using Taylor series method will give us minus QB dash by Cox dash can be rewritten as gamma into square root of psi s e plus 1 over 2 divided by square root of psi s e into psi s minus psi s e. If you see that the square root term is gone away, we have psi s term which is a linear term. So, to avoid the non-linearity, we can use Taylor series expansion to find out some expansion point around which we can linearize our system. Let us go further and simplify our equation. So, we can rewrite this equation as minus QB dash by Cox dash is equals to gamma square root of psi SE plus gamma divided by 2 times of square root of psi SE into psi S minus psi SE. This factor can be written as alpha minus 1 gamma divided by 2 times of psi SE, or you can assume alpha is equals to 1 plus gamma divided by 2 root psi SE. We will explain what is the significance of alpha in subsequent lectures. So, we can rewrite this equation as minus QB dash by Cox dash is equals to gamma times of square root of psi SE plus alpha minus 1 times psi S minus psi SE. Here it is important to note that psi SE is not the potential between psi S0 and psi SL. It is just an expansion point. If you plot this graph, then you will find that between psi S0 and psi SL, I am choosing a point which is an expansion point. So, this is not the physical potential, it is an expansion point around which we are linearizing the system, correct? So, let us use this formula in our basic current equation of IDS1. We know that IDS1 can be written as W by L mu into Cox dash VGB minus V flat band voltage into psi SL minus psi S0 minus half of psi SL square minus psi S0 plus W by L mu of integration of bulk charge. So, instead of taking bulk charge as minus gamma Cox dash into square root of psi S, we will replace this by QB dash is equals to minus Cox dash into gamma times psi SE plus alpha minus 1 into psi S minus psi SE. If you do this integration, you will find that this can be written as gamma square root of psi SE. Now, you are doing this integration between a limit of psi S0 and psi SL. So, you will get psi SL minus psi S0 plus alpha minus 1 is common. The integration of psi S is nothing but psi S square by 2 into psi SL minus psi S0 whole square minus psi SE psi SL minus psi S0. You keep this integration of QB dash between psi S0 to psi SL in equation number 1 and rearrange the term, you will finally get IDS1 is equals to W by L mu into Cox dash into VGB minus V flat band voltage minus psi SE minus gamma into root psi SE plus alpha times psi SE minus psi S0 plus psi SL divided by 2 into psi SL minus psi S naught. In a similar way, if we see the equation of IDS2, then in IDS2 we do have a function which is QB dash for psi SL and QB dash for psi S0. So, QB dash for psi SL can be written as QB dash for psi SL can be written as minus Cox dash into gamma times of psi SE plus alpha minus 1 into psi SL minus psi SE. Similarly, if I am going to write the QB dash for psi S0, I need to replace this psi L by psi S0. And if I am interested in this factor, I will just subtract it from this part to this part, which will give me the closed form equation of IDS2. If you see carefully that we have removed the nonlinear term which is psi S to the power 1 by 2 term from IDS1 and IDS2. We can do further simplification based on the expansion point, in the sense based on the choice of expansion point. Where shall I choose this expansion point? So, based on that we can say our closed form equation of IDS1 and IDS2 can be linearized if we choose some operating point or some expansion point around some operating point. Now we can rewrite the equation of inversion charge as well. Earlier we were writing the inversion charge as minus Cox dash Vgb minus V flat band voltage minus psi s minus gamma root psi s, where Cox into gamma into root psi s is nothing but Qb dash. So instead of writing Qb dash as minus gamma Cox dash into root psi s, we will replace this by our expansion. So what expansion we followed? That Qb dash is nothing but minus Cox dash into gamma into root psi s plus gamma divided by 2 times of root psi s into psi s minus psi s. So we will replace this Qb dash value here, and ultimately this will give me the inversion charge equation around an expansion point of psi s. Now the question is, what is the expansion point we can choose? Based on that, we can define two types of model. One is body reference model and one is source reference model. Let's get an insight into the body reference model. So following this equation, we have found there is a term coming up, psi se minus psi s naught plus psi sl divided by 2. Meaning, if we choose a expansion point exactly at the center between psi s0 and psi sl, or we can take an average, then we can say the expansion point is nothing but psi sm. Here m stands for mean. So we are choosing an expansion point psi se as psi sl plus psi s0 divided by 2. Here I am again mentioning that psi se is not the surface potential between the 0 and L or between source and channel. It is an expansion point used for mathematical simplicity. This helps us to linearize the system. So we use psi se is equals to psi sm is equals to psi s naught plus psi sl divided by 2. If we define alpha, then alpha becomes alpha m, which is nothing but 1 plus gamma divided by 2 times of psi s m. And if we say that we are linearizing out this point, then the slope can be gives us a better accuracy, which is capturing this actual curve. If you see, the actual curve is nothing but this one, where this relates minus Qb dash by Cox dash is equals to gamma times of square root of psi s. So ultimately this is the slope. Here gamma divided by 2 times of square root of psi sm is the slope. How? Because we linearize the system as, or you can take negative sign this side, is equals to gamma times of root psi s plus gamma divided by 2 times of root psi s into psi s minus psi s. So if you see, this is nothing like y is equals to mx plus c, where the slope is this quantity. So this shows the slope of this line, which is nothing but gamma divided by 2 times of root psi s e, right. This helps us to linearize the system. Now if we put back, the simplification will be Qb dash can be rewritten as minus Cox dash into gamma into psi s m and alpha m minus 1 psi s minus psi s m. You put this equation back to your basic equation, ultimately you will get that you have also ignored this term, because you are keeping psi se is equals to this. So ultimately this term will also gone, and hence you will simplify the equation in terms of psi sm by choosing a linearizing point at the center. Similarly, you will get a simple form of IDS2, which is nothing but mu into Cox dash into alpha m phi t psi sl minus psi s0. So I am not putting these equations, you can simply put equations and separate out the variables and you can rewrite the term in this form. If you see closely, we have taken psi SL minus psi 0 out, and this term is a function of VGB. Here psi SM is nothing but psi S0 plus psi SL divided by 2. Let us consider for simplicity to understand what exactly this equation reflects. This is the drain terminal, this is the source terminal, and here the surface potential is psi S0, here the surface potential is psi SL. Now, the moment you increase VDB, or now you consider the VDB and VSB is increases in opposite direction in such a way that the surface potential mean is constant. It means the amount of increase in VDB is exactly same as the amount of decrease in VSB, and hence this factor is not dependent on the horizontal field. Now, if you see this equation, this part of the equation is only governed by VGB, because as we mentioned, we are keeping a scenario such that this is constant. If this is constant, ultimately the value mentioned inside the parenthesis is only a function of VGB, whereas this is a function of the terminal voltage between drain and source. So, you can relate like the current in the MOSFET is nothing but controlled by two sides. One is from the gate. The gate is responsible to cause the inversion, and then the difference between this drain and source causes the carriers to flow. So, we can get the quantity as a function of VGB only, and when we increase VDS, then there will be a current to flow. This is a figure which is plotted between all region model and the model which we just linearized using body reference configuration, and we found that the figure is exactly matching, and hence we can say that the approximation what we followed for body reference model is good enough. Ensuring the continuity outside the inversion, meaning that we are actually saying that we can linearize our QB dash equation, which is nothing but gamma into root psi s into C aux dash in inversion. However, when you talk about the equation which is all region, which is a complete all region model, then it should actually follow in depletion, accumulation and other regions as well. Whereas, when you talk about the accumulation, the QB dash is not that simple. The equation for QB dash is this. When you are talking about the depletion and accumulation, again this expression came by simplifying which contribution is dominant in which region. You remember we wrote QC dash as minus of signum of psi s 2 into q into Na into epsilon s into phi t e to the power of psi s by phi t plus psi s minus phi t plus e to the power of minus 2 phi f by phi t into phi t e to the power of psi s by phi t minus psi s minus phi t. So, this side is the electron dominant factor, this side is the hole and immobile ions dominant factor. So, if you are talking about the linearization of the model, then you should ensure that in which region of operation you are. The linearization what we followed for the body reference model is applicable for inversion region, whereas when you are modeling the current in depletion or in accumulation, then you need to take care the complete model of QB dash, which obviously make the model complex. Let us see another point where we can change the expansion point. if we choose the expansion point as psi s0, then this is called as a source reference simplified model, meaning we are considering the surface potential near the source as our reference point. That is what it is called, source reference simplified model. So if psi sa is psi s0, then what we can write as alpha. So alpha is nothing but 1 plus gamma divided by 2 times of root psi s0. Correct? This is the point around which we linearize, and this quantity gamma by 2 times of root psi sa or psi s0, gamma divided by 2 times of root psi s0 tells about the slope. So if you are choosing this point for linearization, it matters that what is the line you are choosing here. If you choose line A, then it is not predicting accurately this actual behavior. So this was the actual line, and this is the linearized line. So you need to choose the slope accordingly. The slope matters for getting a good approximation of the linearized model. Suppose this factor goes to 0 and hence alpha becomes 1. So you are in this, which is a very bad approximation, which is not capturing the actual behavior of QB dash. Correct? By keeping this value, if you go back in this equation, that QB dash is equals to minus COX dash into gamma root psi SE plus gamma divided by 2 root psi SE into psi S minus psi SE, right? So we have used this equation to put back into IDS1 and we got this expression. Now here what we are doing, to define a source reference simplified model, we are keeping this psi SE as psi S naught. So you can simply get 2 times of psi S naught minus psi S naught. So ultimately here you will get psi S naught minus psi SL by 2, and again separating this term out, you will get the final expression of IDS1 looks like this. Here we also ignored or we also neglected the non-linearity part of term, and the model becomes much more easy or much more simpler than the body reference model. We will see in next lecture that how we can simplify further by considering the slope of this source reference model. Similarly, we can derive the IDS2 part, which is nothing but psi SL minus psi S0 dependent function, and here alpha is nothing but 1 plus gamma divided by 2 times of root psi S0 in source reference model. So let me summarize. In this lecture we found that we can simplify our model by linearizing the bulk charge. We found that in general equation of IDS1 and IDS2, we were getting psi SL to the power 3 by 2 or 1 by 2 term. Similarly, for psi S 0 to the power 3 by 2 and psi S 0 to the power 1 by 2 term, which were making the model complex. To avoid this complexity, we said that why not we will linearize our bulk charge. So instead of taking minus gamma into root psi S into COX dash, we linearize this using Taylor series expansion about a linearized point, which we choose as psi SE. We saw the two cases when psi SE was taken as psi SL plus psi S0 divided by 2, then we called it as body reference model. Accordingly, we found that the simplification in the current equations of IDS1 and IDS2. The other model or other simplification, we found that when psi SE was taken as psi S0, then we called it as source reference model, and we found the simplification in the current equations. So we will stop here for today. Until then, take care.